What if the key to unlocking true artificial intelligence isn't about building bigger models, but about weaving together the very threads of human experience, our thoughts, our sight, and our words, into a single, unified fabric? Welcome to a journey through the forefront of AI research, where we explore a groundbreaking shift in how machines learn to understand the world. Today, we are diving deep into a collection of studies that challenge the status quo, moving us away from isolated, task-specific tools toward a cohesive, multimodal future. We will uncover how new frameworks are merging brain dynamics, visual representations, and language structures into one seamless system. Stay until the end, because the discoveries we discuss today don't just improve algorithms. They redefine the relationship between technology and humanity, revealing a path where AI becomes not just a tool, but a true partner in discovery. For decades, the field of artificial intelligence has operated in silos. We have built magnificent models that can see, others that can speak, and some that can reason, but they rarely speak the same language. This fragmentation has created a ceiling for progress. When an AI tries to understand a complex human scenario, it often stumbles because it lacks the ability to connect what it sees with what it hears and what it knows. Current systems rely heavily on external scaffolds, costly computing environments, and separate modules for every new task. This approach is not only inefficient, but fundamentally limited. It forces researchers to constantly rebuild the wheel for every new application, from retouching a portrait to optimizing a supply chain. The problem is that without a unified core, AI remains a collection of specialized tools, rather a singular, adaptable intelligence. It struggles with the privilege illusion, where models fail to generalize beyond their specific training data, and it incurs massive engineering overhead to verify even simple code corrections. We have reached a point where adding more data or more computing power yields diminishing returns, because the architectural foundation itself is fragmented. But now, a new wave of research is breaking through these barriers. Imagine a model that doesn't just process information, but internalizes the very process of discovery. This is the essence of evolution fine-tuning, an approach that teaches AI to learn from its own search trajectories. Instead of relying on external search algorithms to find solutions, these new models absorb the logic of optimization directly, surpassing base counterparts by over 10% across diverse tasks. It is like teaching a child to fish rather simply handing them a meal. The model becomes self-sufficient in navigating complex problems. At the heart of this revolution is the concept of unification. Picture a single, discrete token space that acts as a universal translator for the mind, the eye, and the voice. This is the promise of frameworks like Brain Janus, which integrates neural dynamics, visual representations, and linguistic structures into one architecture. By using a shared tokenizer, these systems can encode and decode across different modalities without needing separate modules for each. It eliminates the semantic misalignment that plagues dual-stream architectures, much like how a bilingual person can fluidly switch between languages without losing the nuance of the conversation. This unification reduces computational costs and preserves the fidelity of cross-modal reconstruction, allowing AI to understand a song not just as sound waves, but as an emotional narrative paired with visual imagery. Furthermore, this new paradigm is reshaping how we verify and refine these systems. Traditional methods often rely on heavy, isolated environments to test code, creating a bottleneck in development. New approaches, such as the Dockerless verifier, are changing the game by actively exploring repository structures without the need for costly execution environments. This shift improves resolution rates significantly, proving that we can achieve high accuracy without the engineering overhead. Similarly, in the realm of distillation, researchers are finding that dynamic routing of supervision between teacher and student policies mitigates the fragility of standard learning methods. By targeting the least aligned attention heads within a model, we can unlock performance gains that were previously hidden, much like tuning a specific string on a guitar to perfect the harmony of the entire orchestra. The implications of these discoveries extend far beyond the laboratory. We are witnessing the dawn of an era where AI systems are no longer just reactive tools, but proactive partners capable of genuine understanding. By unifying vision, language, and action, We create machines that can navigate the complexities of the real world with a grace and adaptability that mirrors human cognition. This shift promises to democratize access to advanced AI, decoupling high-level verification from technical barriers, and enabling scalable solutions for everything from medical diagnosis to creative expression. It suggests a future where the boundary between biological intelligence and artificial computation blurs, fostering a symbiotic relationship where technology amplifies our own capabilities. As these models become more efficient and less redundant, we free up resources to focus on the true frontiers of innovation, confident that our AI allies can grow and adapt alongside us. As we stand on the brink of this intelligence revolution, it is clear that the future of AI is not about building bigger, but about building better, more connected, more efficient, and more deeply integrated with the fabric of human experience. The research we explored today shows us that by unifying our modalities and internalizing the process of discovery, we can create systems that are robust, generalizable, and ready for the challenges of